Let's now start with our modeling process of the File Transfer Protocol, or FTP, case study. And let's now recall very quickly. So we talk about in the most abstract perception of the protocol in the initial model, we are not going to consider the following facts about the sender and receiver. It doesn't really mean we are never going to talk about them. We will in the later refinements. So we are not going to address the fact that the sender and receiver may simply reside in the geographically distinct locations. The consequence of this is that the file needs to be sent piece by piece, because over the network you definitely are restricted by the bandwidth, so you cannot really transmit the entire file at one go. So this restriction is going to be relaxed in the later refinements. And number two, we are also not going to consider the communication between the sender and receiver by message exchanges. That's also part of the mechanism to really make sure if you try to transmit the file piece by piece, you have to somehow acknowledge from the receiver that they have received certain parts of the file, so the sender would know what else to actually transmit or resend if necessary. And having this in mind, in our initial model, it's going to be very simple. However, it's still going to be useful. Let's see. We're only going to focus on this particular refinements over here. We just want to make sure the copy of the file in its entirety can be sent from the sender and the receiver. We're talking about in the very beginning of the transmission process, the file is in only the sender side. And at the end of the transmission process, the file is entirely copied into the receiver. These are the two snapshots we are talking about, before and also after. What happens in between, we simply abstract it away for this initial model. We don't even talk about how the transmission process is going to be proceeded. That's something that will be left to the later refinements. Just remember that. It's very important to reiterate this concept over and over. So our abstraction strategy will be, we only consider two snapshots over here, right? Let me go over some bullet points with you, and then I will annotate on notes on the iPad. Number one, we want to observe the system with the process of transmission abstracted away. So we simply think about what's going to happen before the transmission and what's going to happen after the transmission. Only these two snapshots. We don't really consider what happens in between. It might take about maybe a few minutes or maybe a few seconds to really go from here to here, but we simply abstract away that duration of time for the transmission process. And we only want to inform from this initial model about what exactly should be achieved by the transmission process. And rather than how exactly the communication or how exactly the asynchrony of the protocol is going to be achieved, we don't really talk about it. Let me summarize very quickly on the diagram over here. This diagram here really nicely illustrates what we meant by the initial model having its transmission being synchronous and also simultaneous or instantaneous. Look at these two parts over here. We got an initial situation is before the transmission happens. We also got a final situation, which is after the transmission has completed. We got initial and the final. So these are the only two snapshots that we consider to really specify exactly what happened after the transmission. But exactly how the transmission happened, we abstract it away and leave it for the later refinements. So we got the sender. You can think about before the transmission and also after the transmission, the sender simply got the same file over here without being modified. That's for the sender side. What about receiver? Before the transmission, the receiver simply got nothing on its end, right? We also assume that there's no buffer in the receiver, so just simply just empty, right? Nothing there. But after the transmission over here, you can see the receiver actually got a copy of the file that's on the sender side, the exact copy over here, right? You can see it's very straightforward abstraction over here. So we simply consider before and after. What exactly is in the middle is simply abstracted away. Let me annotate that. It's very important to see that from this diagram. And we're going to use this diagram many times in the later illustration. So when we go from here to over here, right? So this is really about how the transmission process should really go. Transmission process detail especially how the communication is done between the sender and receiver, and also how the file is really sent piece by piece. They are simply abstracted away. Abstracted away. It is very important to highlight about this abstraction mechanism over here, and we're going to elaborate on the missing details in the later refinements, as I kept mentioning. And let me just fix this one over here. It should be details, plural. Right, let's now go back to the slides. Having this abstraction in mind, how should we define our initial model accordingly? Especially, how do we define the static part? How do we define the dynamic part? Let's see. But before that, let me remind you again that you should really review the contents from lecture number 1 on your own, because we might use some of them in the later refinements, and also a little bit in the initial model already. You want to review about predicates, specifically how you can specify and argue about universal quantification, and also sets relation, and also its various operation. For example, relational image, range, subtraction, domain restriction, and etc. And also the various kinds of functions. For example, partial function versus total function. And let's now talk about, first of all, the state space for our initial model. And the static part, which is very straightforward, so let me just go there directly. We need to define two carrier sets over here, right? Remember we talked about carrier sets earlier. Carrier set is simply just a set of members, but exactly what members are there in the carrier set, it's abstracted away. It's just a set, right? But if we want to specify any particular members in the carrier set, we can define them as axioms, as we saw earlier in the bridge controller. You can definitely refer to it if you got any doubts. We got two carrier sets over here. Let me just annotate them very quickly over here. First of all, the sets over here are so-called carrier sets. Carrier sets, specifically the precise membership. The membership of each carrier set is abstracted away. If you really want to specify some particular member, you will actually have to specify extra axioms if you need it. Abstracted away, right? We keep talking about abstraction. Abstraction is really one of the key words for this course. Membership abstracted away. Over here for the carrier sets. Okay, just to remind you. And we got two carrier sets. What are they? The first one is actually about the data elements over here. So this is really for the data item. And data item can be maybe for single bytes or maybe for single data packets. So here we're not really specifying exactly what they are. And also for the Boolean over here, it's obvious it's going to be a carrier set containing true and false. So that's why you can see this axiom over here is further specified about exactly what this carrier set should be. We're saying that it's by definition simply true and false, only two members. That one's obvious. So you should really think about this one over here and also this one over here. They are related, obviously. And let's see what other static parts we actually got. We also got constants over here. We got n, and also we got f over here, right? So the n over here is about the maximum size. You can think about the maximum size of the file to be transmitted, either the maximum or just the preset size of the file. We don't really assume that you can dynamically grow the size of the file for simplicity. And also the f over here is really about the file that's on the sender side, right? If you look at the initial situation over here in the abstraction, you can see this is the f that we're talking about, right? And the g over here is the file that's to be received from the receiver side, right? So you got f and g. Just don't get confused about what they really meant to denote. So this is really the file on sender. And what about the axiom? We got several axioms over here. We already talked about the third one. Let's see the other two. The maximum size of the file should be strictly larger than 0. So we are not dealing with empty file. And also the file over here is really a total function, right? Let's now do a very quick annotation over here. But you should really review about what a total function is. So that's the part I'm not going to review in the lecture. Over here, you can see this one over here is actually a total function, right? So this is a total function. And you can see the domain of the total function is 1 to n. So we are indexing the different items using the interval set from 1 up to and including n. I'll give you some example in just a moment. And the D over here is some member from the carrier set D. And exactly what members are in D, it has been abstracted away. Right? Let's now see what can be one example of the this total function over here. And also remember, we try to mention in the lecture number 1, you can formalize an array or a sequence using a function. Well, let's see how exactly we can do this. I'll just give you one example. Let me put it here. Let's say example over here. Let's say n is actually equal to 3, just for simplicity, right? And we say that f is actually a member of, let's say 1 up to n. And in this case, we can replace n just by 3, all right? And it's going to be a member of the set of all total functions from 1 to 3 up to and mapping to D, right? And the D over here can be any data, right? For simplicity, let me just say, maybe D contains maybe either D1, D2, and D3, and etc. Okay, so what could be one example function of f? F can simply be, since it must be total over here, meaning that the domain values should really cover the entire set of from 1 to 3. So this is actually an interval set which contains 3 values, 1, 2, and 3. So you can think about, we simply got different pairs over here. It must be 1 maps to something, and also 2 maps to something, and also 3 maps to something over here. And of course, these are simply just the members drawn from D over here. I can just put arbitrarily, I can put D2, maybe D1, and also D3. Doesn't really matter. But what's really important is for you to see this part over here, 1, 2, and 3. The domain of F covers the entire set for this particular set over here, 1 to n over here, right? That's just one example. And let's now move on to the dynamic part for the model. You can see we got variables, we got G and also B. And let me just maybe go over some slides quickly, and then we can come back to do the annotation. Dynamic part, we actually got 2 variables. We got G and also B. The G over here is really the receiver side of the file over here. What about B? B over there is a Boolean variable that we're going to use to denote whether or not the transmission process has completed. Either true, it has been completed, or false, it has not been even started. And we're going to have some invariants. The first invariant is actually very, also we're using the functional notation. It's a partial function, right? You can see this is a partial function versus a total function. And you want to do some homework right away. Go back to your notes in lecture number 1 to see what exactly is the difference between a partial function and a total function. That's why when we were actually back in the math review lecture, I emphasized so much about the difference between partial function versus total function. An answer for you to answer right away. Is partial function always a total function? Or is total function always a partial function? Answer that question first, and then if you cannot really answer precisely, go back to the lecture and check it. Okay. So we're saying that G over here is simply just a partial function from 1 to n, meaning that there might be some missing part from the file. For example, let's see right away. And let's annotate right away here. The symbol over here is about partial function. And you can see the left hand side is still the same 1 to n. The right hand side is still the carrier set for the data items. Let's see the same example. What's going to be changed for the partial function? Let me just put the example over here. Let's say we're still considering n is actually equal to 3. And then we know that G should be a member of 1 to n. And of course, here we can replace n just by 3. I'm just using the same example. as this one over here. So you can really compare and contrast. And then it will be a partial function to the carrier set D. And of course, its membership has been abstracted. And we are still going to use maybe D1, D2, D3. D1, D2, and also D3. And what could be one example for G as opposed to F, right? Being a partial function means that we can miss maybe some values in the domain. Right? That's a very quick, informal way to recap about what a partial function is. So we can say G over here. It could be that maybe so far the receiver have only received items 1 and 3, but 2 is missing. So in that case, we have 1 over here, and also we have 3 over here. And over here, maybe we have only received 1 D2, and also 3 D3. That's all we have received so far from the receiver end over here. And if you look at the domain value for G over here is 1 and 3. Apparently, 1 and 3 over here is a proper subset of this interval set, which is 1, 2, and 3. Right? So that's why it's a partial function. And don't forget, partial function doesn't really mean it always should really miss a value from the domain. And to see why, you should really refer to your lecture number 1. Right? I'm going to rely on you to do that review. We did it very thoroughly with lots of examples in the lecture number 1. Right? So that's about invariance number 1A over here, just about the type of G on the receiver side. And what about the second one? That one is very straightforward. Just saying that B about whether or not the process is completed should be a Boolean. Right? Let me also annotate that for you. So the B over here is really about is a Boolean whether or not the transmission has been completed. True if yes, false if no. Obvious. And we have some little exercises for you to do. Well, of course, I'll give you the answer, but I'll definitely let you pause the video and come up with the invariance. And so these two invariants will be similar to the kind of so-called conditional invariance that we did earlier. If you recall from the bridge controller example, we said that if the traffic light is actually red on the mainland side, that implies something, right? That's kind of the conditional invariant you may have to write in these two cases. But let's take a look what we need to write in the bullet point. So we got these two, which we already discussed. We got number 2 and number 3. So we got 4 invariants in the initial model in total. And we got G, B, we already explained then what they really meant. And also these two are simply just typing constraint, that's obvious. And let's talk about each one of them. Let's talk about invariant 02 first. 02 should really specify what happens before the transmission. Basically, invariant 02 is really about the initial situation. But let me just highlight it, and I'll give you a chance to pause the video and think about the answer. Let me find a slightly darker green over here. So we talk about invariant 02. And that one there is really trying to specify what the initial situation is over here. Okay, over here. And initial situation, as we described before, the sender has certain file F that's kind of standing by to be transmitted. However, on the receiver side, we haven't got anything yet. And how do we specify formally that we haven't got anything for G? For that, you really need to look at the type for G, which is specified as the invariant over here. And how do we know that we are really in the initial situation? We have to look at any of the relevant variable that can actually tell you which situation we are in, either in the initial or the final. Right? Enough hints about how to specify this invariant. Let me remind you again. For invariant 02, it's going to specify what happens or what exactly is the situation before the transmission. Right? You can now pause the video and think about what to fill in for this one here. Alrighty, assuming that you thought about it, and let's see. So this will be the invariant 02. I'm going to put a star over here. Right? I'm going to put it here, because you can kind of combine the visual illustration and the formal predicate together. Well, in order for us to know we are now in the initial situation, we got to look at the value for B over here, right? Because B will tell us whether or not the transmission process has been completed. So initial situation is when the transmission process has not been completed, has not been even started, meaning that the B value over here should be equal to false. As you can see, for B is either Boolean true or false. When B is actually equal to false, what does that entail? That entail basically the sender already got a file standing by, but the receiver has not received anything. How do we specify the receiver has not received anything? Well, that means the file G that's on the receiver side is simply empty set, right? You can think about what's really the smallest cardinality for G. G is actually a partial function. What is the smallest partial function that will satisfy this constraint? Empty set, of course, right? That's something you also need to review about what empty set really is. It's a special case for relation in lecture number 1. So I'll simply say G is equal to empty set over here, right? Let me write a little bit better. Equal to empty set. That's the first one. What about the second one? The second one is kind of symmetric, but we can still let you do the exercise. Once you know about the first one, the second one is rather trivial, but we still do it. Invariance 03 specifies what happens after the transmission. Visually speaking, let's see. Let me use maybe red over here. So we're talking about invariance 23 over here, and we are trying to constrain about what the final situation should look like over here. So this is the final situation, invariance 03. And what should really happen after the transmission has been completed? What exactly should change on the sender side or the receiver side? Sender side, we know that it doesn't really change from here to here, as we said before, but this is the part that's going to change. But exactly how would it change? That will be up to your specification. You can now pause the video and think about what to put for this second invariant over here. All right, assuming that you've thought about it, let's see. For this one over here, it's going to be star over here. And we're going to specify what's going to happen after the transmission has been completed. If it has been completed, so that means the Boolean value over here must have been changed from false to true. So we're going to get B equals true. Right? Remember, either true or false, all capitals, just a convention. In that case, what should it entail? That should really entail, you know what, let me be consistent. Let me just use the red color, red over here. Right? If B happens to be true, in that case, that means the receiver has already received the entire file from the sender side. Meaning that the G over here is exactly equal to F over here. G is exactly equal to F. This is the original file the sender wants to transmit, and after the transmission process has been completed, the file that's at the receiver side should have become just the same, like a copy of the file F. And you can see that's exactly what requirements number 1 is about. So we're talking about the identical copy of the file from the sender to the receiver. So that's invariance 03 over here. Right, so these two invariants are, again, the so-called conditional invariants, as we discussed before, conditional invariants. You want to get used to about how to use the implication symbol to actually specify conditional invariants. Alrighty, let's now go back to the slides, and we have now done specifying the abstract state space for M0.